All right, let's take a look at solving um, a set theory problem using a Venn diagram where we're given cardinal numbers of certain set operations. Our first clue is A intersect B is disjoint. So if you recall what it means for A intersect B to be disjoint, that means there's the number of elements in A intersect B is 0. So where A intersects B is the overlap of A with B, and there are 0 elements in this area. The area is made up of 2 regions, so there's 0 elements in each region. So we've used this clue. Now we're given the information that the number of elements in the set A intersects C is 5. Well, A intersects C is the overlap of A and C. These two areas sum to 5, 0 of which is here, so the other 5 are here. Now we have the clue that the number of elements in B intersects C is 3. So B intersects C is where B overlaps C in these 2 regions, the sum of which is 3. 0 are here, so the other 3 are in this space here. Now we know that the number of elements in the set C without A is 7. So if we take a look at C and we remove A, then we're looking at these 2 regions here. These 2 regions sum to 7, 3 of which are here. So the remaining 4 are in this region. And we've used that clue. Now the number of elements in this set A without C is 2. So if we look at A and we remove C, then we're looking at these 2 regions here, the sum of which is 2. 0 are here, so the other 2 elements are here. We're also told that the number of elements in the universal set is 14. Now the universal set is the sum of every region in the Venn diagram. And if you look, we already have 5, 10, 14. That means in every remaining location, there's 0 elements. And we have used our final clue. So to answer their question, how many elements are in set A, we add the 4 regions that make up set A to get 2 plus 0 plus 0 plus 5, or 7 elements. If we sum the regions that form B, then we have 0 plus 0 plus 0 plus 3, or 3. And the number of elements in C are the 4 regions that form C, 5 plus 0 plus 3 plus 4, which is 12. In this set theory problem, we're given that the number of elements in A intersect B is 5. A intersect B is the overlap of A and B, which are 2 regions. So we can't fill 2 regions with the number 5. We can't use these clues linearly, so we'll just move on to the next clue. The number of elements in A intersect B intersects C is 2. That is the overlap of A and B which was those two sections, and overlap with C, so just this section here. So in that one region, we have two elements. Now we can move back up to the number of elements in the set A intersect B is 5, because again, A intersect B is the overlap of A and B, 2 of which are in this region, the other 3 here. So that we have 5 elements, 3 plus 2, in the area where A overlaps B. Now, where B overlaps C, we're told that the number of elements is 6. So B overlaps C, the intersection, our 2 regions here, the sum of which is 6. So 2 are here, the other 4 are in this region. We're told the number of elements in B without A is 10. So if we look at B, we have these 4 regions. If we remove the regions in A, we're left with these 2 regions, the sum of which is 10. We have 4 here, the other 6 are here. And if you like, we can actually answer already what's the sum of elements in, what's the number of elements in B, right? We have 10, 15 elements in B, summing all 4 regions of B together. Now we have B union C. The number of elements in that set is 23. The set B union C is all of B, all of C, and all of the overlap, right? So B or C or both, which is 1, 2, 3, 4, 5, 6 regions that sum to 23. We're missing 2 spots, so we can't use this yet. The number of elements in the set A intersects C is 7, where A intersects C is the overlap of A and C, these 2 regions. These 2 regions sum to 7, 2 of which are already here, so the other 5 are here. And now, if we want to, we can go back up to this clue where B union C had a total number of elements of 23. Now the 6 regions that made up B union C, right, so shading all of these 6 regions, we have 5 filled, so we can find the missing amount. Here we have 10, 20, and we need to sum to 23. So 3 more elements are in this empty region here. And again, at this point, we can sum the 4 regions that make up C. That would be 5, 10, 14. Now we're given one final clue that the number of elements where A union B union C is our set equals 31. A union B union C are all 2, 4, 6, 7 regions, shading everything except for the outside. We just said that there was 23 in these 6 regions, right? 10, 23. So in our missing region, we have 31 minus 23. For an amount of 8 elements left in this region. Now we can sum the elements in A. The 4 regions of A sum to 10, 15, 16, 17, 18. Remember, when you get your Venn diagram filled out, there's always questions about total. In this one, total elements in A, total elements in B, and total elements in C. All right, let's take a look at this real world problem. 18 cupcakes have frosting and sprinkles. 26 cupcakes have frosting. 12 cupcakes have sprinkles but not frosting, and 21 cupcakes have neither frosting nor sprinkles. How many cupcakes are there? You might think you can just add these numbers together and get the total number of cupcakes, but we'll show using a Venn diagram that that's not the way to approach this problem. If we were just to sum up these four numbers, we'd have 20, 40, 50, 60, 77 cupcakes. However, let's take a look at the clues. If we call cupcakes with frosting S, and we call cupcakes with sprinkles S, then we can use set theory to solve this problem, where we're told that the number of cupcakes, the number of elements in F and S, so remember the and is an intersection, we're told there's 18 cupcakes in this region. Now we have 26 cupcakes have frosting, so the number, sorry about that, the number with frosting is 26. 12 cupcakes have sprinkles but not frosting. So the number of cupcakes that have sprinkles but not frosting is 12. And we also have that 21 cupcakes have neither frosting nor sprinkles. So one way that we can write that, for example, would be S union F complement, and then take the number of elements in that set, which is 21. So now, like our previous problems, we have a list of clues. We can use a Venn diagram then to solve this problem. The universal set, U, will be the number of cupcakes, right? The cupcakes is U. We only need two sets this time, F and S. So this is an example of good naming so that we understand what these are. We could have even called U C. Now what we're looking for is filling in our Venn diagram. So the number of elements in F overlap S, or F intersect S, is 18. And there's only one region that overlaps, where F and S overlap. We also have that the total number of frosted is 26, 18 of which are already here. So if we add 8 more cupcakes, then we'll get a total of 26 cupcakes that are frosted. Now we have S without F. So if we look at S and remove F, then we're left with 12 cupcakes that are just sprinkled but not frosted. And finally, we have that 21 were neither frosted nor sprinkled, right? So 21 are out here in this outer region. So how many cupcakes are there is the question of what is the number of elements in the universal set. That is to add every region in our Venn diagram. So we're going to add the 8 plus the 18 plus the 12 plus the 21. And that gets us 10, 20, 30, 40, 50, 9. So there's 59 cupcakes.